Hello, my name is Jacob Lesperance, and this is my ET 344 class project. So I was assigned the paper on distributed power electronics and enabler for the future grid. So this will be part one of my project. A little bit of background. Electricity infrastructure is the heart of a thriving global economy. The development of the power system was developed in an era when higher speed power electronics were not an option. Today's bloated infrastructure, goals to improve the environment, and a push towards renewable energy leaves us with the inevitable call to action to improve the electricity infrastructure. Power electronics can help us achieve a healthier and more sustainable environment, a more efficient and reliable infrastructure, and a much needed overhaul of the existing grid. High voltage DC, the first need for power electronics. The ability to transfer AC power over long distances was limited by inductive impedance on transmission lines, and the capacitance of the cable hampered underground and undersea cables from transmitting over a long distance. It was then discovered that DC power could be transferred over a long distance. The first HVDC link was built in the 1950s using thyratron devices. Thyristor-based HVDC links require a lot of investing in infrastructure, customizing, and had poor variable power factor with high harmonic levels. Dynamic control. Dynamic control, by definition, is a method to use model predictions to plan and optimize future trajectory for time-varying systems. It is often referred to as model predictive control, or MPC, or dynamic optimization. As systems got bigger, VAR support was needed. Through the development of power electronics, the first fax devices were created to replace traditional control methods. Mainly two things need to be accomplished to achieve dynamic control on the grid: VAR injection and voltage control. Accomplishing these two things will allow us to achieve power flow control in mesh grids, demand control, and higher integration of renewable energy resources. We can achieve these two main things using fax devices, which were created through the development of power electronics and other power electronics technologies. Fax devices stands for Flexible AC Transmission Systems. They're static power electronic devices installed in AC transmission networks to increase power transfer capability, stability, and controllability of the networks through series and/or shunt compensation. SVCs were the first fax devices that provided dynamic control. SVC stands for Static VAR Compensators, and they were created due to the advent of the thyristor. Here's a list of fax devices and their impact on system performance. Power electronics technologies, dynamic power flow control. HVDC Lite offers superior reactive power control, provides independent control of active and reactive power, which creates an improved transfer capacity of the AC network. Created using voltage source converters, or VSC based technology, which was developed through GTO devices like the IGBT. Applications: underground power links, connection of wind farms to the power grid, connecting asynchronous grids, shore power supplies for offshore oil and gas platforms and islands. An extension of HVDC Lite is the multi-point HVDC Lite. which allows the connection between regional and interregional HVDC systems, reduces the number of converters needed to connect multiple sources to the grid. HVDC grids offer an alternative to HVAC systems, which are becoming problematic to build because of environmental regulations. Distributed fail-normal devices. Several devices could be used for controlling a desired narrower range. In power converters, the device would be designed to function in a conventional, non-dynamic control way if the device were to fail or short circuit. Unified Power Flow Controller, or UPFC, is the most versatile fax device. In steady state, it implements power flow regulation, controls line active and reactive power, improves transmission capacity, and in transient state, it offers reactive power compensation, dynamically supports voltage at the access point, improves voltage, damping, and power angle stability. A DSI, Distributed Series Impedance Module. The device used to control impedance can add either inductance or capacitance to the line, which results in the ability to increase or decrease line impedance respectively. And that's based around the DFAX based devices. STATCOM, Voltage Source Converters, or VSCs based fax device, became the new standard over SVCs, which were static VAR compensators. And they were created due to the development of gate turn-off devices such as IGBTs, offered leading and lagging VAR support without issues with harmonics and increased the dynamic performance. Flexible field upgradable transformers. Use of standard distribution transformers while adding extra taps on the low voltage end, and a cooling plate for the electronic module can include a power converter to provide voltage/VAR control for very little cost. When the power converter fails, the transformer acts as a standard function transformer. The module is also fractionally rated, 5 kVA for a 50 kVA system. And here is a nice figure representing that. Grid Edge Volt VAR devices. Edge of Network Grid Optimization, or ENGO devices, act as a fast-acting switched capacitor solution. These devices can be used in conjunction with one another to eliminate variations caused by poor factor loads and improve system efficiency. These devices work on the secondary side of the distribution system. Conclusions. As technology progresses, we will inevitably continue to utilize power electronics to achieve ambitious goals in renewable energy, environmental well-being, economic stability, and consumer reliability. Here are some references. And this is part 2 of my project. Power electronics in microgrids. What is a microgrid? Microgrids are small-scale electrical networks that can work independently or in tandem with large-scale electrical supplies. Microgrids utilize renewable energy resources to provide localized power generation and can be integrated with the utility grid to supply power when demand is high, provide a backup source for blackouts, allow localized electricity in areas where there is limited access to electrical supply. Why use microgrids? Well, they offer sustainable, clean energy. They have the ability to assist the utility grid, can disconnect from the utility grid and work independently, provides an alternative power source where the utility grid is not accessible. It's cost-effective and efficient. One form of microgrids are fuel cell microgrids. Fuel cells convert chemical energy from hydrogen-rich fuels into clean electric power. Electricity, heat, and water is generated by combining hydrogen and oxygen. A fuel cell typically passes hydrogen through the anode and oxygen through the cathode. Like batteries, fuel cells will store electricity, but only while a fuel source is applied to the stack of cells, like a clean natural gas or renewable biogas. Power electronics and microgrids. Often renewable energy sources produce a certain level of current and voltage that does not meet the requirements of the application or load. The voltage output is not constant. In these instances, power electronics and the use of DC to DC converters, voltage regulators, and inverters can be used. Here is a nice figure showing the schematic of a fuel cell and a DC to DC converter, which can boost the signal, the voltage signal from the fuel cell, which would usually be a little bit smaller than you would need for an application, and then the inverter that can convert the boosted DC voltage into an AC usable power supply. Multi-level inverters. These are a power electronics device that can produce an AC voltage output with multiple DC sources as an input. VSC-enabled microgrid. In the case of power outages on the utility grid or low power quality, microgrids can operate in a standalone mode. In standalone mode, microgrids act like an uninterrupted power supply, or a UPS. This is enabled by voltage source converters. And here's a little figure here that you can see how it's connected to the bus line and other components of the grid. Conclusions. Although the main applications for power electronics in microgrids are the use of power converters and inverters, the flexibility and uses for power electronics within the grid are abundant. Here is a list of some of my references. And thank you for listening to this presentation, and I hope you all have a nice day.